look at some various raster formats and displays, especially those represented by 3D data displays. So 3D data not only includes an X and Y value, but it also includes a Z value. Digital elevation models are famous for having these X, Y, Z values because that's the grid value, the grid cell value of each one of the grid cells. But once we put something like a digital elevation model into the GIS, then we can, for example, drape an aerial photograph on top of that, or we can put our roads to match those values of X, Y, and Z along the digital elevation model. For the example with the aerial photograph, sometimes we call draping that 2D data onto a 3D surface. But the other thing that we can do is we can take 2D features that have a base height, like a building, and then we can pull those up or extrude those into the third dimension in order to make a display. Digital elevation models are a common way to represent 3D data. And with digital elevation models, this is colored so that the highest elevations are in white and the lowest elevations are in this bluish green color here. They create an overall surface, and once again, on top of that overall surface, we can assign any values of raster, vector, or imagery data to this three-dimensional surface and come up with some interesting three-dimensional displays. Voxels are similar to digital elevation models, but they're a little different. Instead of each one being a grid cell, each one is a volume element or a voxel, which also has a height associated with it. So for example, if we were looking at how groundwater is traveling through the ground, we might be able to build a 3D model in which all of these blue cells represent where the groundwater flow is the fastest, or something similar to that, where we're actually concerned with not just a surface like elevation or topography, but we're actually interested in a volume, such as where groundwater is underneath the ground. Another thing that we often see in GIS is these point clouds. These point clouds are often associated with LiDAR data, which stands for light detection and ranging. And basically it's light that's bounced from some sort of UAS or airplane down against the ground, and the returns from that are measured by sensors on the plane, and then we know how far from the plane's location those points are, and we can make kind of this 3D model based on that, where each one of these is a little point with an X, Y, and Z coordinate, and we can clearly see where the bridge is here and the tops of some of the buildings and the land. All of those things stand out by their differences in elevation. So these are often colored based on the elevation, and we're able to kind of see a 3D rendering of the area in this way. Another way that 3D data is stored is as tins, and this would be once again back to kind of surfaces like an elevation surface from a digital elevation model. A digital elevation model is great, but in an area like this we may have hundreds or thousands or millions of individual grid cells that are just kind of defining this area where maybe the elevation doesn't change that fast. But if we find those areas where there are changes in elevation, we assign points to those, and then we draw triangles in order to come up with a surface that would have a continuous slope in that area. That's the triangle that goes into these tins or triangulated irregular networks. They're called irregular because all of the triangles are different sizes based on how quickly the elevation is changing. But they cover the land completely, just like the grid cell does, and each one of the points, once again, would have an X, Y, and Z location, and from those we would have areas of continuous slope, which is how steep they are, and aspect, which is which direction they are facing. Another thing we can add to our map is multi-patch features. These would be something like buildings or maybe oil refineries or other objects that we want to put on our map. But we're not just extruding a 2D layer from the GIS up. We can add things like kind of this beveled surface here if we want to, and can do much more in creating these multi-patch features that we want to include on our map to represent different things that we might have that stretch up into or extend up into the third dimension. Another way that we can represent data on a map is instead of using the third dimension for height, we can use the third dimension of our map for time. And if we do something like this, we create something that's called a SpaceTime Cube. So this SpaceTime Cube has specific X, Y locations, and then time would be going up in this direction here as we go higher and higher above the land. And what we could measure any sort of different thing here, such as this shows the intensity of shaking associated with an earthquake, and the darker areas are where more intensity was felt. So we can just kind of map something like this throughout a volume, which is X and Y, and then T, or time, as we go up above the land surface here. This is possible in the GIS, but of course, just like many other things, the data has to be properly formatted to do this. So we need the proper formatting of date-time fields in order to do something like this, where we put it out into a special format, this netcdf format, which is specific to SpaceTime cubes. We have to know what the time increment is as we're moving up, and set some other things here, as far as what attributes it's reading from the attribute table, this time field, and then we're able to make a SpaceTime cube, as was shown in the previous example.